Hi, everybody, and thanks for coming. Um, this is the first of what we hope will be several different webinars that we're going to make during the shutdown period. Hopefully, everybody will get a chance to learn something today and learn something throughout the shutdown period. A couple notes: we're recording the webinar, and we'll send you the slides and the recording afterwards in case you have anything you want to review. And if you have any questions during the slides, there's a question and answer box on the Zoom, so you can type your question into the Q&A, and I'll try to answer them in real time if I see them, and otherwise I'll save them for the end. Today we're talking about balance, and differential signaling. For those of you that don't know me, I'm Doug Jorgensen, the VP of Engineering at Marki Microwave, where we've been making Baluns for the entire history of the company, mostly in mixers, and then somewhat separately in as standalone products for the last several years. So I'll start with the first and obvious question: why bother balancing a signal? Why screw with a balanced signal at all? So balancing allows you to, it gives you the magical property of eliminating unwanted filter signals without using a filter. So typically the only way that you can differentiate signals is by using a filter to frequency discriminate. But if you used balance, oh, can you guys hear me okay? Okay. Thanks. There's no feedback. So if you use differential signaling, then you can eliminate unwanted signals without filtering. And so in a balanced mixer, it allows you to isolate the ports and suppress the even order spurious products. When you're using signaling, for example, backplane differential signaling, it allows you to eliminate unwanted differential common mode noise. And in circuits like silicon CMOS circuits, like analog to digital converters, you can eliminate the common mode noise as well as even harmonic products and IP2. So using a Balun is just one method of using differentially phased signals. And the way that the other ways that you can do this are on this slide. Anytime you use a split signal circuit topology, it gives you improvements in power handling. So if you're talking about maximum power output or maximum input power, P1 dB, IP3, some types of harmonic generation, anytime you split the power, you'll get a 3 dB improvement if you split the power in half. So the different ways that you can do this, you can split it in phase, and that is typically the best for increasing power because it's the lowest loss. There's no complicated coupling structure. So especially over broadband, in-phase power combining gives you the maximum increase in power output. If you, on the slide, I'm using mostly amplifiers to illustrate this, but it could be anything. It could be a limiter or an attenuator or a 50 ohm load. It could be a lot of different things in the middle of these. If you're talking about a balanced amplifier, typically what people mean when they say balanced amplifier is a quadrature phase amplifier. And in a quadrature phase amplifier, you can eliminate the reflections from the input because the reflections from both amplifiers are matched. And let me see if I can point to this. No. The reflections from both of the amplifiers are matched, and so they're terminated in these 50 ohm loads at either side. If you're making a balanced amplifier using a Balun, typically the phrase you use is a push-pull amplifier. And the push-pull amplifier, it gives you all the power improvements that the in-phase and quadrature phase balancing give you. But it also eliminates common mode noise and especially even harmonics and IP2. So the most common reason for our people to use a push-pull amplifier is to increase the IP2 of an amplifier. And that's only really interesting in broadband applications, which means that it's only interesting when you use a broadband Balun. And when you use a broadband Balun, you typically get a degradation in the power to the point that it's not usually a power efficient thing to do. And the last type of signal combining I want to talk about is what I call mixed phase. This is where you have an unbalanced input looking into a balanced output, or an in phase looking into an out of phase, or an out of phase looking into an in phase. And this is a technique that we use at Marki occasionally for improving the suppression of fundamentals mostly. So you can, if you have an in phase looking into an out of phase, then you eliminate the input signal and you can collect the harmonics instead. So there's a tech note that we've got on our website about using this technique for nonlinear transmission lines. And typically a nonlinear transmission line will give you every harmonic output. But if you balance them in this mixed phase method, then you can eliminate every other harmonic, for example. So that's what you can do with Balun and with differential signaling. Let's talk about the Balun itself. What is a Balun? What does a Balun do? A Balun is a mode converter between a balanced signal and an unbalanced signal. And the word Balun itself is a portmanteau of those two words, Balun, balanced, and unbalanced. Balun. A passive Balun of the type that Marki makes and sells is differential, or is bidirectional, meaning that you can go from differential to single-ended, or you can go from single-ended to differential. Roughly equivalently, we'll talk about why that is not necessarily always true a little later. You hear Baluns described as Balun transformers, and the reason for that is that the impedance on the input and the impedance on the output can have different relationships. So the input is typically always either 50 ohm or 75 ohm for cable TV systems, but the output can be differential. It can be 100 ohms differential, meaning that each balanced side is 50 ohms to ground. It can be 50 ohms differential, meaning that each balanced port is 50 ohms or 25 ohms to ground. And the way that this is described is with the impedance ratio. So if it's 50 ohms in and 50 ohms differential, that's 1:1. If it's 50 ohms in and 100 ohms differential, that's 2:1. And you can also have some 4:1 Baluns that is not something we make, but you can buy them. One factor I'm going to talk about that people I think underappreciate in Baluns is isolation. The isolation between the two balanced ports, between the two differential ports. If you have a high insertion loss between the differential ports, then it improves the performance of the Balun in ways that we'll see. And the most important specs for a Balun are how well it is balanced. So an ideal Balun would create two copies of the input signal where one is inverted relative to the other, but both were exactly aligned in time and had the exact same amplitude. And the way that we characterize the ideality of a Balun is using the amplitude balance and the phase balance. So a good Balun, a homebrew Balun that you might design on a circuit board over broad bandwidths can provide, plus or minus 2 dB of amplitude balance, and we try to hit half a dB of amplitude balance, and typically provide at least 1 dB across the full bandwidth of our Baluns. And in phase, so amplitude is the easy one. It's the size of the signal. Phase is the time delay between the two signals that manifests as a radial, delay. And good Baluns provide 15 to 20 degrees. Marki Baluns, we try to get to 5 degrees. And typically our max is around 10. If you combine these two factors mathematically, you can calculate what's called the common mode rejection ratio. The common mode rejection ratio is how much of a input signal, if you're doing a single-ended to differential conversion, how much of the input single-ended signal shows up as a common mode signal at the output, and vice versa. If you have a differential mode signal going in, how much of the differential signal shows, how much of the common mode signal is rejected by the Balun. And a typical circuit, a good circuit is 15 to 20 dB. We target around 25 dB or higher. All of the graphs that I'm showing are for the BAL 0009 SMG for this presentation. So the way that we, for a 3-port power splitter, the way that we would usually describe the performance is with single-ended S parameters. If we're talking about a Wilkinson power divider or a quadrature hybrid or any device like that, we talk about the single-ended S parameters. What is the insertion loss from the input to the output? What is the return loss from the input to the output? Where it treats every connector as a port. There are some problems with using this way of describing Baluns. And the problem is that typically a Balun is not used as a 3-port device. It's used as a mode converter, where it's actually a 2-port device where one port has 2 modes. And so the way that the mathematical formalism that is best for this is mixed mode S parameters. So for some examples of this, if we're talking about the common mode rejection ratio that we showed on the last slide, if you're looking at mixed mode S parameters, that jumps right out of the S parameters. That's just the conversion from the single-ended port to the common mode of the differential port. The differential port is 1, the common mode is 2. So it's S21SC. If we're talking about the insertion loss of the Balun as a mode converter, if you look in the upper left, you see the insertion loss of the device as a single-ended. If you treat it as a single-ended component, the insertion loss is around 7 dB across the band. If you look at it as a mode converter, though, the insertion loss is 4 dB because you lose 3 dB per side, but then you get it back if you're combining it together, and assuming that the phase is correct. And the last one, which is probably the most important one, is the match of the differential port. How well matched is the differential port to the output? Typically, the way you describe this is with the return loss, right? How close to 50 ohms are ports 1 and 3? And that should be described by the return loss of output 1 and output 2. But if you look at the third graph over, you see that those ports are well matched on their own. But if you look one more to the right, you see S11DD, that's the differential return loss, is very bad. It's worse than 6 dB across the band. So how is that? How is it that you can have 2 well-matched ports that when they're excited together creates a large return, a large reflection? The reason is isolation, which is what I mentioned before, the insertion loss between the 2 differential ports. So I got a question. The question is common mode rejection the same as image rejection ratio? Essentially, it is. Image rejection ratio is something that you calculate from an image rejection mixer based on, but the way you calculate it is based on the vectorial cancellation of the 2 signals. The common mode rejection is slightly different. I'll talk about this. I'll give a more detailed answer at the end, but it's a very good question. So isolation, the insertion loss between the 2 ports of a differential, the 2 differential ports of a Balun, is very important. If you are doing a differential to single-ended conversion, or if you are doing a single-ended to differential conversion into a reflective device. And the reason is that even though the 2 ports are well matched, they crosstalk with each other. And so if you do a simple experiment, if you take 2 Baluns, put them back to back, and you measure them with a VNA or with a time domain signal, you would expect it to just look like a cable. Ideally, it would just look like a cable. But what you see instead is this ripple in the insertion loss and the ripple in the return loss. And in the time domain, you get these humps in your data signal. And the reason is this standing wave. So I got a question about the mixed mode S parameters. Are we using a true differential VNA to make the measurements? Usually the VNA is single-ended. So that's what I'm saying sort of on this slide, which is that, so if you have isolation, you can smooth out the S parameters and you can eliminate all of the return loss ripples. What this means is that you can do really advanced testing. So you can, if you're just looking at linear S parameters of a passive device, you can 50 ohm load the ports and back calculate all of the linear parameters with a 2-port VNA. You don't really need anything fancy. But if you're trying to do anything interesting, then you're probably looking at nonlinear measurements. You're probably looking at the power compression, the harmonic generation, things like that. And that is something that requires a true differential VNA. So a true differential VNA uses two sources and creates a 180-degree phase shift between them using, fancy signal generation techniques that VNA people know that I don't know. But it creates, it acts as a perfect Balun as on the input. And that allows you to do single tone, power generation, harmonic generation, power compression, linear measurements. But if you're trying to do more complex measurements than that, two-tone, multi-tone, spurious, and especially things like eye diagrams, bit error ratio, EVM, harmonic distortion, spectral regrowth, actual, testing with real signals. There's not, to my knowledge, there's not a signal generator that can produce all of these different signals differentially. And that is where a Balun is somewhat required to take true differential nonlinear measurements. So that brings me to the promised top 3 mistakes that people make when they're using differential signaling and Baluns. The one we just talked about, I put as number 3, the lack of isolation, doing differential to single-ended conversions. Number 1 is the classic rookie mistake, which is length matching. Anytime you're trying to do any kind of phase matching, this is probably something all you guys know, you have to make sure that your cables are phase matched, your connectors are phase matched, everything. I recommend you tape everything down to the table, or else you'll get temperature wander and walk off and stuff like that. Anytime you have a differential length, it shows up as a linear phase walk off is what you see with the phase walks off with frequency in a linear way. That means that it's just a time delay. And the second one is something that we run into a lot with analog to digital converter people, which is they'll have an 8-channel board. They're trying to capture 8 different channels. And we always have to ask about isolation first, because if you have two differential channels next to each other, then to far away traces, if you have 2 channels far away, then the attack will look different, will look common mode. They'll see basically the same thing, and it can be rejected by the device. But for 2 nearby channels, you have to be very conscientious about what the isolation is between your 2 neighboring traces. Okay, now we're going to take 1 minute for a quick quiz and a quick poll. So, how familiar are you with mixed mode S parameters? How many people have ever heard of mixed mode S parameters before? Never heard of it, up to fluent. What is the benefit of a push-pull amp? We talked about this on the 3rd slide, I think. Does it cancel out harmonics, improve the return loss, maximize output power, or improve IP2? And what mixed mode S parameter gives the common mode rejection of a Balun? Is it S12DS, S12CS, S11 DD or S22SS. I'll give you another 30 seconds to talk to answer these. And then we're going to start talking about the different types of balance that there are out there and what they can do for you, and especially focusing on the types of balance that that Marki Microwave makes. Okay, a couple votes still coming in. Okay, that's half of the people. So I'm going to share the results with you. Most people have read about them once, so this is the second time that you're hearing about mixed mode S parameters. We're planning to revamp our Balun data sheets to really feature the benefits that mixed mode S parameters can give you. So hopefully people will become a lot more fluent with these. The benefit of a push-pull differential amp, most people got it right. It is you improve IP2. You can improve your output power, but it's not typically the maximum output power that you get. And the return losses are typically the same. And what mixed mode S parameter gives the common mode rejection of a Balun? Again, most people got it right. That is S12CS. So 1 is the differential port, and C is the common mode of the differential port, and then 2 is the single-ended port, and S is the single-ended port. Anytime you see S11 or S22, that's a return loss. So good job. Thanks, everybody. Now we're going to talk about balance. We're going to talk about the different types of balance. So common mode choke. The most common type of Balun in the world is a flux coupled Balun transformer. This is the same type of transformer that you get at a power station, and the operation of it is pretty straightforward. You have one coiled wire goes in, generates a magnetic field. It's wrapped. A second coiled wire is wrapped around the same magnetic core, and the magnetic field induces a current in the second wire. So all the coupling is provided by the magnetic field. This provides ground and DC isolation, which is something that none of our Baluns do. You have completely separate DC systems on each side. The bandwidth ratio can be massive, from like very low, hertz or kilohertz up to gigahertz. But the downside is that they're limited to around 3 gigahertz. You typically don't see these devices go higher frequency than 3 gigahertz. Now, they're the most ubiquitous Balun in the world, and they're great, and I wish they worked all the time, but they don't go high enough in frequency. So the next step up, you have to go to a transmission line. You can't treat the signals as lumped anymore. So with a transmission line Balun, anytime you take a transmission line and you ground one side, you'll get a balanced output. And I'm showing it with a bifilar, but you can use any arbitrary transmission line will produce this effect. It's not that good because it's very noisy. There are a lot of reflections and resonances. There's a very problematic half-wave resonance, and it doesn't go to very low frequency. So the solution to this is to add some magnetic material and wrap the transmission line around the core somehow, and that creates a transmission line transformer Balun, which is many of the types that Marki makes. Many of these. It's got a very broad bandwidth ratio, and the high frequency can extend beyond 10 gigahertz. It's lossier than a flux coupled Balun transformer typically, but it goes to higher frequency. And this is the type that you see in our lower frequency module Baluns and our lower frequency surface mount Baluns. And our newest product in this line is a 10 megahertz to 12 gigahertz small form factor surface mount Balun. We've got a lot of requests from customers to reduce the height and to reduce the width of the Baluns, and so we have heard that, and the new Balun should be coming out anytime soon. The next type is the one that we produce probably the most of by number, because these are our mimics and our microlithic type balance. This is what I call a coupled line based balance. So again, you take a coupled line section, and you float the ground. There are a lot of different circuits. I'm showing a march-on Balun on the right there, but there are a lot of different connections that you can make between coupled line sections. And if you look at Chris's, HFSS library, you'll find hundreds and hundreds of different versions of these coupled lines simulated for different reasons. And the great benefit of these is that they can be integrated. They can be made planar. I'm showing a spiral Balun. That's very, very common in the lower left-hand side. And you can combine the spiral Baluns in many different ways. The problem with these is that the low frequency is limited to 1 to 2 gigahertz. You can't get below 2 gigahertz because it's a quarter wave problem. You don't have the magnetic material to extend your quarter wave down. So it really restricts you. But in terms of the size that you can get and the scalability, these can't be beat. And our newest product, in terms of bandwidth ratio, we've just released our broadest band coupled line Balun, which is the MBAL 0220 SM. It's a surface mount mimic 2 to 20 gigahertz surface mount Balun. And it's really a great accomplishment to have a 10-to-1 ratio mimic Balun on the market. The last type I'm going to talk about that we make is a power divider phase shift or power divider inverter type Balun. And to do this, you have to be able to make a super broadband inverter, which is sort of like a magnetic core type material that creates a negative version of an input signal. And then you just match that with a delay line. You match it in amplitude and in time with a delay line. And then you use a power splitter, and it can be any type of power splitter. It has to be an in-phase power splitter, and then the output is balanced. And in our case, we use a super broadband Wilkinson power divider, and that means that we have very high isolation between the two ports. So this can be super broadband because the inverter is so broadband. So the flagship product that we have in this product line is the BAL 67, which is 300 kilohertz to 67 gigahertz with high isolation. If you're doing any kind of chip measurement or characterization activity, this is the preferred solution. And the last type I'm going to talk about are Baluns that we don't make, that maybe some of our competitors make, or maybe you can make them yourself. The easiest Microwaves 101 Balun is a rat race coupler. It's very easy to design and fabricate. The performance, like I said, you can get pretty decent performance, 15 dB common mode rejection pretty easily. It's sub-octave bandwidth that all makes it uninteresting for us. But if you guys need a Balun, you want to design your own, then that's a good circuit to go with. The second one is the asymmetric tandem coupler. So all of these circuits that I'm showing on this slide are 180-degree couplers, which means that they can be used as Baluns, but they also have an isolation or a sum port. So you can collect, for example, the even and the odd harmonics of something, and you can collect them from different arms. The asymmetric tandem, we've looked at it, and we don't like it because it's got that weird impedance discontinuity. If you look on the right hand side, there's not really a way around that. It's hard to lay out, and it's just not a very practical circuit in our opinion. But some of our competitors make this. Maybe if there's an application for it, let us know, and we can make it. But typically when somebody asks us for a 180-degree coupler, they really want a Balun and don't use the isolation port. And the last type is the waveguide Magic T. This is the original OG, MIT Rad Lab Magic T. Waveguide companies make them. They're high isolation, low loss. They can be really great. They're limited by the bandwidth of the waveguide, so you get all the problems that you have with waveguide. But if you're already in waveguide, then don't bother converting. Just use a waveguide Magic T. If you look at our catalog on the website, you will see we break our balance into two different major types. One is what we see as system balance, so surface mount and bare die balance. These are for analog to digital interfaces, D to A interfaces, silicon, clock driver inputs, balance circuits, push-pull circuits, and antenna feeds for things like phased array antennas. And the other type that we advertise is what we call test and measurement balance. These are all connectorized module balance that you would use for component measurements and laboratory experiments, chip characterization, things like that. As always, our mission is to help you guys design faster, simplify your production, eliminate complexity, and shatter performance barriers. If you go to our website, you'll find a primer that I wrote a number of years ago on balance that's got this information and more. A lot of tech notes, including a tech note dedicated just to mixed mode S parameters, which I think everybody needs to read. Videos, we're always available on support@markymicrowave.com. And we'd like to thank you guys for coming. Please, when we send out the email, the follow-up email, register for our upcoming webinars. In 2 weeks, we're going to do amplifier biasing made easy. Jacob and Rob, our amplifier team, is going to do that. And then 2 weeks from that, Harley and Chris are doing a brief guide to mixer spurs, all about how to predict mixer spurs, how to prevent spurs, and everything related to that. So thank you for joining. I hope you learned something today. Stay safe and healthy. And I'm going to spend a couple more minutes answering the questions that I've got. If you guys have anything else that you wanted to ask, I'm going to stick around. But that's all of my prepared material. So thanks for coming. Have a good day. So I'm going to stop